Now, how does all of this work in a living cell? Obviously, cells are not beakers and they're not plastic boxes that are open to the environment. Cells are enclosed, wrapped by a membrane. So if a lot of water were to rush into a cell through osmosis, that cell would swell up and even rupture. Conversely, if a lot of water were to exit a cell through osmosis, that cell would shrink down and even collapse. Osmosis, therefore, is something that can be very dangerous to living cells. What we'll talk about now is the process of osmosis in living cells and this related concept of tonicity. The good news about osmosis in living cells is that they do have the ability to deal with a relatively small amount of osmosis. In other words, as long as there are no large shifts of water through osmosis, cells can tolerate a little bit of swelling and a little bit of shrinking. But if osmosis were to occur in any large amount in a cell, the results could be disastrous. The results could lead to the death of the cell. Take a look at the diagram on this slide. This represents different osmotic events around a living cell. If you start over on the right-hand side of the diagram, up at the top, you're looking at a representation of a cell here. And I know it's a little bit hard to see, but the artist has drawn in that there is a fair number of these green particles inside the cytoplasm of the cell. Here is the membrane encircling the cell. And then there are green particles outside of the cell. We're supposed to see that the green particles are approximately the same inside and outside this cell. You'll notice these blue arrows here that have arrowheads on both sides. What the arrows are representing is the movement of water. Now, water travels across a cell membrane, again, through simple diffusion and facilitated diffusion, actually all the time. In other words, even when there's no concentration gradient, there's going to be movement of water into and out of cells, just all the time. The important thing is there's no net movement of water in either direction. So the cell doesn't swell up, the cell doesn't shrink down, everything just stays the same. Water moves in and out constantly, but there's no shift in large volumes of water. If you follow down to the bottom of the diagram, you can see that over time, this cell doesn't change size at all. It doesn't swell up, it doesn't shrink down, because there is no concentration gradient of this green particle. Now look at the center diagram. If you start up at the top again, you'll notice that the number of green particles inside the cell has increased, and the number of green particles outside the cell has decreased. Now we have a concentration gradient. Now imagine that this green particle cannot cross this membrane. Maybe it has a charge on it. Maybe it's way too big. Maybe it's too polar. But for whatever reason, the green particle cannot cross the membrane using simple diffusion. That means there's a concentration gradient here that cannot resolve through the particles moving. Water is going to respond. Now, water, remember, is going to flow in a direction towards the high concentration of green particles. So water will travel from the side where there are very few green particles across the membrane to the side where there are lots of green particles. And the idea is that the water is trying to dilute out this high concentration of particles and bring it down to the same concentration that's outside the cell. You can see that the blue arrows now don't have heads on both sides. The water is moving, again, in both directions, but there's net movement into the cell. A large volume of water, in other words, is traveling into this cell, and this cell is going to swell. If you travel down to the bottom of the diagram, you can see what happens as a result. The cell can swell up to a point without having any problem. In other words, small volumes of water can travel into a cell and cause it to swell slightly, and the cell will be fine. The cell won't suffer any damage as a consequence. But there will come a point where an increase in the volume inside this cell is going to push out the phospholipids in the membrane to the point where the membrane ruptures. This gets a name. We call this cytolysis, or more simply, lysis. When a cell ruptures like this, it's called lysis. And of course, this cell is now dead. If you go over to the last two images on the left, we're looking at something similar to what's happening in the middle. It's just happening in reverse. In this panel, the number of green particles is lower inside the cell and higher outside the cell. And again, if this green particle cannot cross the membrane, we have a problem here because there's a concentration gradient of green particle and it cannot resolve. So water is going to move here through osmosis. The arrows are showing us that the net movement of water is from the inside of the cell, where there are very few green particles, out to the outside of the cell, where there are a lot of green particles. The water is trying to dilute the large concentration of green particles outside the cell. Now, a small amount of water can leave a cell without damaging the cell. But if a large shift occurs and a large volume of water leaves this cell, the cell is going to collapse down on itself and the membrane will be damaged till eventually the cell dies. Living cells can tolerate osmosis in small amounts, but anything more than that will damage and even kill the cell. Take a look at the image on this slide. This image was taken using a light microscope, and it shows red blood cells that have undergone osmosis, where water ran out of the red blood cell to the outside. I want you to take a look at how the membrane around these red blood cells has changed. It's got little spikes on it almost. It's got these little spicules, these little projections coming off the membrane. It doesn't look quite as obvious as this, but you can definitely see that there's something abnormal happening with these red blood cells. These red blood cells are shrinking inward. The membrane is collapsing inward. We give this situation a name. This is called crenation. Crenation is defined as this state where a cell becomes shrunken and develops a notched or indented edge. That's a good way to think about it. It's notched, it's indented, it's collapsing in on itself. And crenation is not good. When crenation occurs, there will be a point where the cell membrane can no longer function normally. And that red blood cell, which is critical to delivering oxygen, is not going to be able to do its job. On this slide, you can see a really nice electron microscope image of two red blood cells that have undergone crenation. These two cells have lost so much of their volume that the membrane has just collapsed in around the reduced amount of cytoplasm, creating these projections. These cells were in a situation where there was a high concentration of some molecule outside of the cell compared to the inside of the cell. The molecule, in other words, had a concentration gradient and was not able to resolve that gradient. So osmosis occurred. Osmosis caused water to flow out of the red blood cell and into this environment where there was a high concentration of particle. And that movement of water caused the volume of cytoplasm to go down and down and down until this crenation occurred. Now let's discuss this concept of tonicity and how it relates to osmosis. If you translate this word, tonicity, it translates as tone. So tonicity is a measure of tone, and it specifically describes the tone of the solution around a cell. Now, by tone, what is meant is how many molecules are dissolved in the solution around a cell. If there are a lot of molecules in the solution around a cell, we call that high tone or high tonicity. If there are very few molecules in the solution around a cell, we call that low tone or low tonicity. Now, there are more technical terms for high and low tonicity. We use the term hypertonic to describe high tonicity and hypotonic to describe low tonicity. The key thing to remember is that tonicity describes the environment outside of the cell. A lot of people use tonicity to describe both the inside and the outside of the cell. But technically speaking, when we talk about tonicity, we're talking about the environment outside of the cell compared to the inside of the cell. So let's think about these terms separately. Hypertonic means high tonicity. Lots of molecules, in other words, are present in the solution outside of the cell. You can think of that as meaning high tone. Remember, whenever we use the term, we're comparing the outside of the cell to the inside of the cell. So another thing that we can say is that the concentration of dissolved molecules in the solution surrounding a cell is higher than the concentration of that molecule inside the cell. That means the cell is sitting in a hypertonic solution. Now, hypotonic is essentially the opposite. When a cell is sitting in a hypotonic solution, that's a solution that has a low tone. In other words, the concentration of dissolved molecules in the solution surrounding the cell is lower than the concentration inside the cell. The last term is this term isotonic. Iso means equal, so equal tone solution. The concentration of dissolved molecules in an isotonic solution is the same as or equal to the concentration of dissolved molecules inside the cell. These are the three states of tonicity that we need to be familiar with. Let's go back to this diagram that we looked at a couple of minutes ago, where we saw this drawing of these cells in different situations of tonicity. The tonicity of the solution around a cell is going to determine which way osmosis will occur. Remember, osmosis is occurring in a particular direction in order to dilute out the side where there are more molecules. So, if a cell is sitting in an isotonic solution, that means that the number of particles that are dissolved outside of the cell is the same as the number of particles inside. We have no concentration gradient here. No osmosis is going to occur. If a cell is sitting in a hypertonic solution, it's a very different situation. That means there are more particles sitting outside of the cell than there are inside. That means water is going to flow from the inside of the cell to the outside. Water is going to flow out of that cell. And finally, if a cell is sitting in a hypotonic solution, there are fewer particles outside of the cell compared to the inside. Water is going to flow into this cell. Osmosis is going to occur inwards. Now look at the diagrams. The right side diagram again, this represents a cell sitting in an isotonic solution. Water is still moving here. Water moves constantly into and out of cells. But in an isotonic solution, the concentration of these green particles is the same inside and outside. There's no concentration gradient. And if there's no concentration gradient, there is no net movement of water, either into or out of the cell. The cell is sitting perfectly happy. No water shifts are occurring because it's in an isotonic solution. The pictures in the middle represent a cell sitting in a hypotonic solution. Remember, tonicity is about the outside relative to the inside. This cell is sitting in a hypotonic solution. The number of particles outside is less than the number of particles inside. If the particle cannot resolve this concentration gradient, water will. And water will flow towards the side where there are more particles. So water will flow into the cell. Osmosis will occur into this cell, and the cell will swell. The last panel represents a cell sitting in a hypertonic solution. There are more particles outside compared to the inside. If the particle cannot resolve this concentration gradient, the water will resolve it. Water flows from the side with fewer particles towards the side with more particles to dilute out that high concentration. So in this panel, osmosis will move water out of the cell. The cell will shrink and eventually collapse upon itself. Now let's think about osmosis and tonicity in the human body. Remember, we've said that humans have anywhere from 60 to 75% water in their body. It's not pure water, though. It's salt water. It's saline. And we've said that the concentration of the sodium chloride inside the human body is about 0.9%. That's what we mean when we talk about saline, or what's sometimes called normal saline. It's a concentration of 0.9% sodium chloride. That means the water inside of your blood, the water inside of your blood cells, the water in all of your cells, in all of your tissues, has a concentration of 0.9% sodium chloride. Now, if I were to put an intravenous solution into your vein, and that solution contained 0.9% sodium chloride, I can call that an isotonic solution. Remember, tonicity is about the solution outside of the cell compared to the inside. So if I'm putting in a solution with 0.9% sodium chloride, I'm putting in an isotonic saline. If I were to put a solution into your vein that had a higher concentration of salts, greater than 0.9%, I would be giving you a hypertonic solution, because the amount of salt in the solution is higher than what's inside the cells. Hypertonic saline. And finally, if I were to administer a solution that had less than 0.9%, I would be administering a hypotonic solution. The number of particles in that solution, the number of salt particles, is less than what's inside the cell. Obviously, in medicine, we use isotonic solutions because we don't want to cause osmosis under most conditions, right? We want to prevent osmosis from occurring. So we administer isotonic saline when we want to add more volume to the blood, when we want to hydrate someone. I do have a question at the bottom of the slide, though, and I want you to give this a little thought. Can you imagine a medical emergency when the temporary administration of a hypertonic saline would make sense? Can you imagine a situation, a particular emergency involving a human being, where putting a solution into their vein of hypertonic saline would actually make sense? Hypertonic saline, so it has a high concentration of sodium chloride, higher than what's inside the blood cells. Give that a little bit of thought. I'm going to post the answer in our discussion board called Questions, Questions, Questions.